This video gives you an introduction of voltage control in power systems and the different methods to control it.
So far we have studied that power system is operating under steady state conditions and working normally. The meaning of this is that the load demand is steady, so the system is working normally with all its technical constraints within limits. However, the real and reactive power demands are never same, that is never steady and keep on changing continuously. So under steady state conditions, there is a balance between the power generation and power demand. However, if there is a mismatch of active power demand, the machine's speed will vary with consequent change in the frequency, which is highly undesirable. The maximum permissible change in the frequency is plus minus zero point 0.5 Hz. In India, this variation band for the frequency lies between 49.5 Hz to 50.2 Hz. Frequency should remain constant because the power stations run in parallel and in synchronism. Similarly, if we talk about the voltage, we know that the voltage at various buses must remain within the prescribed limit. And the permissible voltage variation band is plus minus 5% or 0.05 per unit. If the voltage go beyond these limits, there will be reactive power mismatch. So what we can see from this discussion that voltage and frequency are the two parameters that needs to be monitored and that needs to be controlled every time, because the violation of any of these parameters will lead to the unstable operation of the power system. So voltage and frequency controls are necessary for the effective operation of power systems. Frequency fluctuations are detrimental to electrical appliances because there are a lot of reasons that there has to be the frequency deviation should be within limits. For example, if the load is three-phase AC motor load which runs at speeds directly proportional to the frequency. So if there is a variation of system frequency, this will affect the motor performance. Also for voltage, both the over voltage and under voltage are detrimental to the electrical appliances. Over voltage can cause insulation failures in machines. Electrical motors which are running on over speed when fed with a higher voltage will result in vibration and mechanical damage. Also, when the motor loads are supplied with less voltage for a specified power rating, the current drawn will be more and this will give rise to the heating problems. Therefore, it is essential to keep the system frequency constant and voltage variation within the tolerance. Also, we know that frequency is a global parameter, that is, it has to remain same throughout the system, and the voltage is a local variable or a local problem to be handled. That active power is dependent on the internal machine angle delta and is independent of the bus voltage, while bus voltage is dependent on the machine excitation and therefore on the reactive generation Q and is independent of the machine angle delta. Any change in delta will cause a change in the generator speed. Let us consider a two bus system shown in the figure, and conditions for the real power and reactive power at the receiving end has been again written here, which we have already derived earlier while doing the calculations for the complex power over a transmission line. Here the bus number 1 has been denoted by the angle delta and the magnitude Vs, which is the sending end, and the bus 2 is the receiving end. At the bus 2 a load is also connected and the load is also having demand of PD plus JQD. Now if you look at the expressions of P and Q at the receiving end, we can see that the active power depends upon delta and the reactive power depends upon the change in the voltage magnitudes. Now under steady state conditions, we know that the power balance is maintained, which has been written here neglecting the losses, that the PR will be equal to PD, means the power which has been delivered from the bus number 2 to the load, active power and the reactive power will be equal, that is the generation will be equal to the load. So the equations has been written here for steady state. PR equal to PD and QR equal to QD. Now suppose the load demand has changed. It may increase or decrease, and the balance which has been shown by PR equal to PD and QR equal to QD, let these be disturbed because PD may increase or decrease. Similarly, QD may increase or decrease at the load end. So this will result in imbalance of these equations. So if PR is not equal to PD, it means that there is a problem of frequency violation, and if QR is not equal to QD, means there is a problem of voltage violation on the system. If real load demand increases, that is if PD increases as compared to PR, then there is a need to increase the generation, which will be done by increasing the steam output of the turbine. Controllers that are used to make PR equal to PD again are known as the speed governors. The reverse happens when the real load demand decreases, then the frequency will increase. Again, the speed governors will be required to bring back the balance between PR and PD. Similarly, if we see that there is an increase in the reactive demand QD, then the voltage at the receiving end will drop, and vice versa will happen in case when the reactive demand is reduced, the voltage will increase at the receiving end. So again, we require some controllers to bring back a balance between the reactive power generation and reactive power demand, that is QR equal to QD. So in this chapter, we'll be discussing how voltage and frequency control can be done. So first we'll take the voltage control, and later on we'll go to discuss the frequency control. Voltage control means that we are controlling the reactive power, and similarly when we are controlling frequency means we are controlling the active power of the system. Now for every utility there are certain objectives that needs to be met out for its reliable and efficient operation. Both the utilities and customer equipments are designed to operate at certain voltage rating, and also the prolonged operation outside the allowable range of the voltage could cause damage to them. Therefore, the voltage at the terminals of all the equipment should remain within the acceptable limits. Also, for the stability to be maintained for a system, the voltage levels and reactive power control should be there, because otherwise it will be having the negative impact on the system stability, and the system then will not work normally. Before jumping to the methods of voltage control, we'll have an idea about how the different elements of the power system respond to the reactive power. For example, overhead lines are there. They, depending upon the load current, they can either absorb or supply the reactive power. At the loads below the natural load, that is surge impedance, the line will produce a net reactive power, and at loads above the natural loads, the line will absorb the reactive power. Similarly, if you look at the other elements like transformers, they always absorbs the reactive power regardless of their loading. And the loads which are connected to the or acting as the load buses, they normally absorb the reactive power. Loads at low lagging power factors will cause excessive voltage drop in the transmission network and are uneconomical to supply. It has to be noted here that reactive power Q cannot be transmitted over long distances, so the voltage control is done using special devices dispersed throughout the system. Let us now look at the different methods of voltage control, and hence the control of reactive power which can be done on the system using the different components or the devices which are there. The first one is synchronous generator itself is a primary source of voltage support. It can generate or absorb Q depending upon the excitation. But because the synchronous generators are the machines which will be located at the PV buses only, so in order to control the voltage at other buses which are not the PV buses, we need some additional means to control the voltage throughout the system. So the voltage needs to be controlled locally by using some additional elements or additional devices into the system known as compensating devices. These devices should be sources or sinks of the reactive power, like shunt capacitors, shunt reactors, synchronous condensers, tap changing transformers, and the static var compensators SVCs, which is a part of the FEX devices. The compensation of the transmission line is done in two ways, either in series or in shunt, where the compensating devices will be connected either in series with the line or in shunt with the line, in order that whether they require the plus Q into the system or the minus Q into the system. The shunt capacitors and reactors and the series capacitors provide the passive compensation. They are either permanently connected into the system or they are in the switched form, where they can be switched in steps when they are required. Shunt capacitors and reactors will contribute to the voltage control, and the series capacitor will help in improving the transmission efficiency and stability of the system. Synchronous condensers and the static var compensators SVCs, they provide the active compensation. The reactive power absorbed or supplied by them is automatically adjusted so as to maintain the voltages of the buses to which they are connected. The performance of EHV AC transmission systems can be improved by reactive compensation of series type. It consists of capacitors connected in series with the line at suitable locations. Series capacitors reduce the series reactance of the lines and act as the line compensators. The compensation of lines helps in improving the system stability and increases the transmission capacity, that is efficiency of the system. The power transfer capacity of a line can be given as P is equal to EV by X sine delta, where delta is the torque angle. Now here we can write the expression with and without compensation. With compensation means when the series capacitor has been connected into the line, how the power flow will be changed. So we can write an expression P1 without compensation and P2 with compensation in the EHV lines. Now when the series capacitor is connected to the line reactance get modified, and if you look at the expression of P2, it will be now written as the net reactance of the line will be XL minus XC. Now this factor is now overall reactance is reduced as compared to P1. So if you take a ratio P2 by P1, we can write this as 1 upon 1 minus XC by XL. Now here the ratio XC by XL is called the compensation factor and is usually denoted by K, known as degree of compensation, and it is sometimes represented as percentage also, known as percentage compensation. The typical values of K lies between 0.4 to 0.7. It's always less than 1, and for the economic degree of compensation, this lies between 40 to 70%. Now suppose K is equal to 0.5. So if you calculate the ratio P2 by P1, it comes out to be 2, the meaning that the power transfer is doubled by 50% compensation. Another advantage of series capacitor compensation in the line is the improvement of the system stability. So we can see that for the same amount of power transfer and same values of E and V, the delta in case of series compensated line is less than that of the uncompensated line. So if you calculate the ratios of delta 2 by delta 1, which will be written in terms of the reactances of the line, and this delta 2 will come out to be lesser, and we actually need less value of delta, which means better system stability. Now we have already read the chapter on power system stability. Now it might be clear to you that the value of delta should be less for steady state stability, and even for the transient state stability the value should be lesser than 180 degrees. Now we will discuss the shunt compensation, wherein the different compensating devices will be connected in shunt at the receiving end. Suppose there is a heavy loading condition, means the reactive demand has increased as compared to QR. This means the voltage will drop at the receiving end and net Q will be negative in this case, means line is absorbing Q. So it means the plus Q is needed in order to balance QR equal to QD. So we need shunt capacitors in this case. This is also called peak load condition, where the lagging power circuits are created. In case of off-peak load conditions or light loading conditions, the reactive power demand is less than the reactive power supplied. That is, QR is more than QD. In such situation, the voltage at the receiving end will increase. That is, VR will be greater than VS. And if we calculate the net Q, it will be positive. It means the line is actually supplying Q. So minus Q is required to meet out the condition of balance between QR and QD. So in this case, shunt inductors are needed. Now let us see another type of shunt compensation using a rotating VAR generator. This is also an active compensation. Now in this, a synchronous compensator is connected, that is a synchronous motor running without a mechanical load and having an excitation adjustable over a wide range. Depending upon the value of excitation, it can either inject or absorb reactive power. It feeds positive VARs into the line under overexcited condition and feeds the negative VARs when underexcited. A figure shows the synchronous motor connected to the receiving end bus bars and running at no load with an adjustable excitation. The compensator can automatically run in overexcited mode when there is a high loading conditions and can supply the required reactive power, and it can work in underexcited state during the light load conditions, and in this situation it will absorb the reactive power. This is a rotating VAR generator. The name is synchronous compensator or synchronous condenser, and it is normally connected to the tertiary winding of the transformer connected at the receiving end. The formula for QC is given to find the plus VARs or minus VARs which will be supplied by the machine. So when EG is greater than VR, it's an overexcited case and the machine will be feeding plus Q or plus VARs into the line. If EG is less than VR, it is an underexcited case and the machine feeds minus VARs or minus Q into the line. Now another way to control the voltage or the reactive power is with the help of the tap changing transformers. The receiving end voltage and hence the reactive power can be controlled by changing the taps of sending end and receiving end transformers. Such tap changes are done on load either manually or automatically, and hence the transformer are also called tap changing under load transformers. The voltage drop in a line is supplied or compensated by changing the secondary EMF of the transformer, done by changing the number of turns. The operation of a transmission line with a tap changing transformer at each end is shown in the figure. Here TS and TR are the fraction of the nominal transformation ratios, that is the tap ratio by nominal ratio. To compensate for the voltage in the lines, the transformer taps are set at off nominal values TS and TR. The value of TS is taken as greater than 1 and TR is less than 1 for voltage drop compensation. The normal tap setting range is usually not more than plus minus 20%. By adjusting the taps, the voltage can be controlled and hence Q can be controlled.